Now that we have some idea of how star systems form, we can turn our attention to the formation of our own solar system. When we look around our solar system, we got to remember there's a few characteristics that we want to keep in mind. For starters, everything orbits the sun in the same direction. That is, if we were looking at the solar system from, let's just say, overhead, everything would appear to be orbiting the sun in a counterclockwise rotation. But there are some exceptions to this rule, and that is comets. Sometimes the occasional comet will seem to come in a clockwise direction, as seen from overhead. Otherwise, yeah, everything's orbiting in the same direction. Another thing to think about is that if you look at the planets as they're arranged from the Sun out to, say, the orbit of Neptune, it turns out that these planets all seem to orbit the Sun in roughly the same plane. That is essentially what we now think of as the ecliptic. But beyond Neptune, you see an abundance of highly inclined objects. These are the dwarf planets, the Kuiper Belt objects, and so forth. They seem to be a bit tilted above and below the plane of the ecliptic. So, if we're going to put together a model of how the solar system formed, it's important that whatever we consider has to reproduce what we currently see today. And astronomers have a pretty good hypothesis as to how our system formed. We believe that our solar system formed within a cloud like you see here. There was once upon a time a rotating disk, and as this disk was coalescing around the proto-sun, which is depicted at the center, there became little instabilities within the disk. The disk fragmented, and clumps formed within the disk, giving rise to the ultimate formation of today's planets. And these protoplanetary disks are fairly common. Sometimes we see them edge on, or sometimes we see them nearly face on. But when seen at microwave wavelengths, as we have here on the right-hand side of our screen, you can make out the distinctive rings and spoke-like features of this disk. So this is significant because it means that there are protoplanets inside this protoplanetary disk that are beginning to sweep out the concentrations of gas and dust within their orbits. So as we gaze around the solar system, we find there's a variety of objects, namely giant planets and terrestrial planets. Giant planets are composed of mostly lightweight materials, what we call volatiles. For example, this is dry ice, frozen carbon dioxide, and frozen ammonia. So we're going to have these very lightweight materials such as hydrogen, helium, methanes, and chlorofluorocarbons, all cold enough to become an ice. And it's for this reason that these planets have a relatively low density. But terrestrial planets, on the other hand, have relatively few of these lightweight elements, and they're mostly composed of rocky or refractory materials, so minerals, olivines, and so forth. So why then are these two types of planets so very different from one another in terms of their composition? And the answer goes back to the formation of the planets themselves. Remember, it all formed inside of a disk that you see here. So if we think about this depiction of our proto-solar system, we have an abundance of refractory materials starting from just around the protosun all the way to the very edges. There's plenty of silicates, plenty of carbonates and minerals and so forth. However, it is not until you get past, say, the orbit of Mars and toward the orbit of Jupiter that temperatures drop low enough that volatiles can condense, water, molecular hydrogen, and so on. In other words, they freeze out. They become solid enough, or at least slushy enough, in order to fully condense. And in fact, once you get out past the orbit of Saturn, the temperatures are low enough to even allow high volatiles such as hydrocarbons, methane, ammonia, and so forth. They can even start to condense. So the point where the temperatures drop low enough is called the frost line. It's really just the distance where the temperatures are low enough for volatiles to condense. And so, why then are the small rocky terrestrial planets closer to the sun and the large gas and ice giants farther from the sun? It's because of that temperature difference. It is only in the outer solar system where these large planets can form because they have an abundance of both refractory and volatiles. However, inside the solar system where the terrestrial planets live, there are only refractory materials to build with. So how does a spinning disk of gas and dust go on to become planets. Well, in order for us to think about that, we have to change our perspective. We have to go deep inside the circumstellar disk, and instead of thinking about the disk as a whole, we need to change our scale and get smaller and smaller until we are finally at the scale of individual grains of dust. So, these dust particles will go on to become planets. Here's how they do it. First of all, the dust particles are not the same exact kinds of dust particles that we think of in our rooms and in our houses. Dust in space is mostly composed of silicates and chondrites, whereas the dust in our rooms is composed of dead skin cells, insect feces, and so forth. Well, since there are no people or insects in space, we are left with a slightly different kind of dust. Nevertheless, these fine dust particles do carry an electric charge. And just as particles of dust and dirt carry electric charge in our rooms and cling together to become dust bunnies, so do these particles as well. They become cosmic dust bunnies. As a matter of fact, they can grow quite large, and they do so by just undergoing very gentle collisions, which allows them to grow into rocks, then into boulders. Anything harder or faster would break these things apart. But as these things grow, they can withstand harder and stronger collisions until they grow into what are now called planetesimals. At planetesimal sizes, at about 1 kilometer, they're massive enough to exert a gravitational pull on one another. This means that they can withstand harder collisions. And in fact, we see leftover planetesimals around the solar system today. They are modern-day asteroids and comets and Kuiper Belt objects. And these planetesimals collide in a kind of proto-solar system demolition derby. Most of these are destroyed and are later accreted onto other planetesimals. And the most massive of these planetesimals survive and are now protoplanets. They begin to clear out their orbits. You can even do a simple computer simulation like we have here, and you can easily see how as objects collide into one another, there are fewer and fewer of these objects remaining. And so when we look in systems like TW Hydrae, we can actually see those rings. We can actually see those lanes being carved out by protoplanets within the disk. So returning our attention to the gas giants, remember, they too are forming out of little disks within the disk. Remember, they're going to form well beyond the frost line, where there is a high abundance of both refractory elements and volatiles, so they have everything. They gain mass by just colliding with additional planetesimals, and because they have more mass, because they're now proper protoplanets in their own right, they're able to accrete these volatiles. Remember, they're farther from the protostar, so there's less heat, there's less stellar wind, and there's a greater abundance of these volatiles to begin with. So an accretion disk forms around the protoplanet. It's like a disk within a disk, and even moons can evolve from inside the protoplanet's own accretion disk. And this allows these massive outer solar system protoplanets to grow what are called their primary atmospheres. And that means that the atmospheres of Jupiter and Saturn, for example, are the same atmospheres that they pretty much formed with. However, in the inner solar system, where we have lower mass protoplanets, it's a much different situation. They are unable to hold on to those primary atmospheres. Remember, the temperatures are much warmer near the protostar, or in this case, the protosun, and hot gases are going to always move faster than cold gases. So if you have a low-mass planet with low-mass gases, they can easily achieve escape velocity from those gases. Remember, the hotter they are, the faster they're going to be moving. And they're also closer to the protosun. That means that there's a stronger stellar wind coming from the protosun, which just makes it that much harder for these lightweight volatiles to stick to the protoplanets. So any protoplanetary atmosphere of the inner solar system is just going to be blown away by the sun. However, there's a lot of smaller objects floating around in the solar system, and even from the outer solar system. And when little tiny planetesimals from the outer solar system fall toward, let's say, proto-Earth, they deliver these volatiles, and there's already volcanism on the planet. So now we get the formation of a secondary atmosphere. So, about 4.5 billion years ago, the hot Earth was really just one giant volcano. The entire surface was covered in volcanism, and whatever trace volatile materials the Earth did form with were quickly being released through volcanism, and comets and asteroids would deliver additional volatiles from the outer solar system. So, our atmosphere that we live under today is the second atmosphere, the 2.0 version of Earth's atmosphere. So, to put the whole thing into perspective, we can imagine that rotating disk and we can envision tiny clumps of material forming inside that disk. And those clumps would then go on to become planetesimals and even protoplanets. Protoplanets would then have the ability to start sweeping out their orbits as the sun was undergoing its final fitful phases of its own formation. Protoplanets began to scoop up and sweep up their orbits, thus clearing their paths, giving us the solar system we live in today.